All right, trig integrals. Okay, last time there was a problem at the end that we dealt with that involved the cube of secant, and it required us to know a fair amount about the secant function and its relationship to tangent, yes? We actually had to use integration by parts to pull that one off, right? And we ended up with a fairly interesting looking answer at the end, but in the end we were able to pull it off, which was great. So we looked at secant, secant squared, secant cubed, and now the question naturally arises, what if I have other powers of other trig functions? How am I going to deal with those? And that's what this section is all about, is dealing with powers of trig functions. Okay? So, you know what, I'll fix it if I need to, but I'm just going to go, I am going to do a slideshow. It just looks a lot better. Okay, sorry. Okay, so trig integrals. So again, this is dealing with integrals with powers of sine and cosine, and integrals with powers of secant and tangent. These are the two that really seem to come up most often. Okay. And finally, the last thing we do in section 3 of chapter 8 is we deal with integrals that happen to have products of sines and cosines where the angles are actually different. Like for instance, you might have sine of 3 theta times cosine of 4 theta or something. Does that make sense? That's like, what on earth do I do in that situation? It turns out, believe it or not, that comes up more frequently than you might realize in practice. Mathematicians don't just sit around. Well, they do sit around and come up with obnoxious things. But, something like products of power or products of sines and cosines with different angles, they didn't come up with that just willy-nilly because they thought it would be interesting. It actually does come up in practice. And so it's something that we're going to deal with in this particular section. Okay? All right. So first, let's deal with products of powers of sines and cosine. Now, one thing there's basically 3 identities that you need to keep in mind when dealing with these. One is the so-called Pythagorean identity, namely that sine squared plus cosine squared is 1. That's known as the Pythagorean identity because it comes from a right triangle on the unit circle. Do you realize that? Like, sine and cosine are defined as the x and y coordinates of a point on the unit circle. Well, you can draw like a right triangle there, and sine and cosine are the legs of that triangle, and the hypotenuse is the radius of the circle, which is 1. So leg squared plus leg squared equals hypotenuse squared. Yes, that's what the Pythagorean theorem says. And so sine squared plus cosine squared equals 1 is known as the Pythagorean identity. Okay? The second and third identities that you're going to want to use are the so-called half-angle formulas. Half-angle formulas. Sine squared equaling 1 minus cosine of 2x over 2. I don't know what to do about that. You just have to straight memorize it, okay? And cosine squared is equal to 1 plus cosine of 2x over 2. Yeah? You probably have seen those before. The reason they're called the half-angle identities, well, I don't know. Why do you think they're called the half-angle identities? Well, but it's half. Okay, well that's interesting. Okay, yeah. Well, I mean, there's halves all over the place, just like there was yesterday on the board at some point. But there's actually another reason it's called the half-angle identity. Yeah, sir, Jacob.
Because sine and cosine each form part of the 93.
You guys are like way too sophisticated for my tiny brain. It's simpler than that. Look at the angle on the left-hand side. It's x, yes? The angle on the right-hand side, inside of the cosine function, is, yeah, so the angle on the left-hand side is half the angle on the right-hand side. That's why it's called the half angle identity, okay? But yeah, those are great observations. I hadn't really thought about that before. But that's why it's called the half angle identity. By the way, there's another one called the double angle identity, where the thing on the left has angle twice that on the right, yes? That's why they're called the half and double angle identities, okay? So these three things right here are the key to doing what we're going to be doing. And our goal is to somehow deal with integrals of products of powers of sines and cosines. We should be able to handle that, okay? It says where at least one of m and n is a positive integer, okay? So, I mean, if they're both 0, that's stupid. That would just be the integral of dx. We know how to deal with that, right? It's only interesting if one of the two, or maybe both of those powers happen to be positive integers, okay? Here's some guidelines, okay? I mean, we could kind of think this through and come up with it, but I think it will make sense once you see these guidelines in practice, all right? If one of the powers is odd and positive, okay? Okay, so that would be like the powers like 1 or 3 or 5, etc., right? If one of the powers is odd and positive, keep one of that type of trig function and convert the rest to the other kind. You might be saying to yourself, what? What is going on here? Okay, convert the other to the other trig function by using the Pythagorean identity, and then expand using substitution and integrate. Because basically, okay, if I had a power of like 5 on the cosine function, okay, then I could peel off one of the cosines. Like if I had a cosine to the 5th power, I could peel off one of the cosines and put it at the end. And then how many cosines would I have left? It would be cosine of the 4th. And then I could basically think of that as cosine squared. You know what I'm saying? And then I could actually replace cosine squared with 1 minus sine squared. Do you know what I mean? And then you can make a substitution because I have that extra cosine sitting outside. Don't worry, we'll have lots of opportunity to play with this thing, okay? Now, okay, that's what happens if one of the powers is odd and positive. If one of the powers is odd and positive, that's what you do. Peel off one of them so that the remaining power is even, and then you can use the identity to turn everything else into the other trig function, and then you do a substitution, okay? So again, odd, peel one off, replace the rest with the other one, and then you're off to the races just by doing a basic use substitution. 2, if both, okay, so look, number 1 handles any situation. You understand what I mean? Number 1 handles any situation where I have an odd power somewhere. If I have an odd power on both sine and cosine, then it's like, oh, happy day, I get to choose which one I peel off. Does that make sense? Okay. If you have an odd power anywhere, number 1 is our guide. What's the only case left to deal with? Both even. If both powers are even and non-negative, you're like, huh, wonder what I'm going to do. Well, in those cases, you use the half angle identities to convert the integrand to odd powers of cosine, okay? Because one thing you may have noticed, if I go back, look at that. If I see the half angle identities down here, notice that the power 2 of sine becomes a first power of cosine. Does that make sense? So the second power of sine becomes the first power of cosine. And a second power of cosine becomes a first power of cosine. So there's a way that we can kind of decrease powers. Does that make sense? And then we can put ourselves back into number 1 again. Okay? So these are the two guiding principles that we'll use. And of course, we're going to do lots of examples to that end. Yes, sir. So it says if both powers are even and non-negative, You use the half angle identities to convert the integrand to odd powers of cosine. Okay? Why? Because if you have like sine to the second power, then if I use the half angle identity, what am I going to have now? It's not going to be sine to the second power anymore. It's going to be cosine to the first power plus, plus some other junk that I can deal with, right? So that's kind of the thrust of what's happening. You decrease the second power to the first power in cosine, and then you will have an odd powered situation, and you can proceed just as we did before, okay? Don't worry, I mean, all this will make sense once we actually see it practically work out. But that's how it's going to go, okay? Other questions? Other questions? Well, yeah. Let's look at some examples, all right? And hey, maybe this would be a great time to have you kind of partner up with someone next to you and sort some of this out. So here's a first example, just kind of thinking through what we just talked about. Here's a first example. Okay, so here we go. Here's an example. Okay, example. Okay, integral of, let's do sine to the fifth power of x, okay, times cosine to the fourth power of x dx, okay? I'm gonna let you work on that on your own, okay? Just kind of remembering the guidelines we just laid down together. So sine to the fifth power times cosine to the fourth power. Oh. So think about that on your own for about 5 minutes. Talk to people around you and see what you come up with. Okay, that's not quite right. You need to write that as sine squared. Yeah. All right. All right, let's talk about this. So what do we say? We had, so the good, I would say that number one was kind of like the good situation, right? This is the one where we had an odd power somewhere. It seems, and when I say peel off one of them, what I mean is kind of set it aside. Then you will have an even power on what's left. Okay? So what is it? I mean, I was kind of listening in, eavesdropping on some of your conversations. So what do you peel off in this case? Right, you peel off a factor of sine. Okay, and so you write this as sine to the fourth of x, cosine to the fourth of x. Okay, and I like to just sort of put the sine function at the end, sine x dx. Okay. So far, so good. And then the second admonition was to then replace the remaining sines, in this case, with cosines, yes? But how does one do that? What do I do with this, the sine to the fourths? The sign that we set aside is going to stay there for the purposes of doing a substitution later on. But what do I do with the remaining sine to the fourth? What do I do? Okay. Yeah, that's okay, right. So kind of an intermediate step is to write this as sine squared, because I want to replace sine squared with its cosine equivalent thingy, yes? So if this would have been, instead of sine to the fourth, if it was sine to the 10th, what would I have done? Sine squared to the 5th. Does that make sense? What if it would have been sine to the 50th? Sine squared to the 25th. You understand what I'm saying here? You want to get sine squared isolated underneath a power so as to replace it with its cosine equivalent. Okay? So then it's cosine to the fourth of x, sine of x dx. Fine. Now what? Yeah, that's right. So you go integral. Okay, so it's going to be 1. Okay. Sine squared plus cosine squared is 1, which is the same thing as sine squared being 1 minus, 1 minus cosine squared of x. And this thing is being squared. Cosine to the fourth of x, sine of x dx. You say, oh, wow, that looks way more complicated than what we started with. But now we're in business, because what can I put u equal to? Yeah. If I put u equal to cosine of x, what is du? Negative sine of x. Okay, which I mean, look, I don't, we have a sine x dx. We don't have a negative sine x dx. So, I mean, I would be inclined to like move the minus sign to the other side, okay, and turn this into a plus, yeah, okay. All right, and now we're ready to make a little substitution here, okay. The minus sign I can just pull out front. So it's going to be minus the integral of what? 1 minus u squared times u to the fourth du. And you might say to yourself, oh man, now what do I do? Well, I mean, I would just be inclined to expand this thing. Does that make sense? Like, this is one of those situations where the better part of wisdom is to simply use algebra to finish the job here. So let me just I won't go through the whole thing, but if you expand this thing out, it's going to be 1 minus 2u squared plus u to the power 4 times u to the fourth du. And now what am I going to do? All I did was just square that thing out, right? Yeah, just distribute this thing through here, and then etc. You could figure it out. That's going to be simple. Does that make sense? You're just going to have a bunch of powers of u that you can easily integrate at this point. Okay. So hopefully it makes sense how to finish the job on this thing. Got it? Got it? Any questions on that? And there's no stopping you now. If you have an odd power at all, by the way, I would be inclined, like if I had a choice between an odd power on sine and an odd power on cosine, I would be inclined to work with the odd power on cosine. Why do you think I would be inclined to do that? Yeah, because then the negative symbol doesn't become an issue. Does that make sense? Here, the negative sign became an issue, but we didn't have a choice. Here, we had to work with the odd power on sine. You work with the odd power on cosine, I'm telling you, you're going to end up putting u equal to sine, and the derivative of sine is straight up cosine with no negative symbol whatsoever. So that would be, I think that's slightly less obnoxious. Okay? Yeah. All right. So let's go back. Okay. Second, if both powers are even and non-negative, use the half angle identities to convert the integrand to odd powers of sine and proceed as in guideline 1. Okay? So any odd power at all, you're going to proceed precisely as we just did in that first example. The second situation is where you find yourself without an odd power. You find yourself in a situation where it's an even power in both cases. Okay? Oh, right. We're in the examples phase right now. Okay, so hang on. So let's go back. And let's go back in here and we'll do another example. Okay? All right, so here we go. What do I want to do? I want to go to the next one here. Yeah, there we go. All right. So here's an example. Very simple. So example, integral of cosine squared of x, sine squared of x, dx. What are you going to do? What are you going to do? And by the way, half angle identities. So let me just kind of write these down for you just so you have them in your back pockets. Remember, we had, they were right here, right? Sine squared, the way I like to remember it is the sine squared thing comes with, there's like a minus sign on the cosine, yes? The cosine squared half angle identity, there's a plus sign on it. But other than that, it's exactly the same. Either 1 minus cosine 2x all over 2, or 1 plus cosine of 2x all over 2. Okay? So we'll kind of write that down up here so that you have it as your reference. Okay, so sine squared of x is equal to 1/2 1 minus cosine of 2x, and cosine squared of x is equal to 1/2 1 plus cosine of 2x. Yeah? All right. So kind of work on your board there and see what you come up with in this case. Be interested to know. Okay? Go for it. Right? All right. Any progress here? So what did you get for sine squared? I mean, so if you just plug in the half angle identity straight up, I'm going to get a factor of 1/2 from each, right? So what am I going to be able to pull out overall? What constant am I going to be able to pull out front? 1/4 integral, and then it's going to be 1 plus cosine of 2x, 1 minus cosine of 2x dx. Okay? Isn't that a product of, like, if like you have a plus b and a minus b? Isn't that just the first thing squared minus the second thing squared? If I multiply that out, the cross terms cancel, right? The inner and outer terms cancel. So, like, think about this. You have 1/4 integral of what? 1 plus cosine of 2x minus cosine of 2x minus cosine squared of 2x, right? dx. And you say to yourself, okay, hey, I still, what now what? I know how to do the first thing, so watch. This obviously is going to be, 1/4 times the integral of 1 dx, which is very easy to do, minus 1/4 times the integral of cosine squared of 2x dx. Right, I just kind of broke that thing up, distributed the 1/4, yes, okay. But what do? I clearly know how to do the first thing. That's easy. That's just x times a fourth, right? But what about the second thing? What on earth do I do there?
Would you, yeah, use substitution for the 2x and then the 1/2, does that work? No.
Maybe that might be too complicated. Is there something? Why not just use the half angle identity again? Yeah. So what's cosine squared of 2x equal? It's 1/2 times what? 1 plus. Think about it. Just cosine of 4x, right? Like 2x is going to be half whatever the angle is in here. 1 plus cosine of 4x. Make sense? Okay. Interesting. So if I plug that in, that's going to turn that 1/4 into what? Right, so it's going to be 1/4 integral dx, which I know how to do, minus 1/8 integral of 1 plus cosine of 4x dx. And do you know how to do everything now? Do you know how to integrate 1? Yeah. Do we know how to integrate the second one? Yeah. Yes. What about cosine of 4x? Is that very hard to integrate? No, it's basically 1/4 sine of 4x. Why would it be 1/4 sine of 4x? All right, the chain rule, right? You could do a U substitution if you wanted to kind of sort that out entirely, but you know how to do all of these, right? So let me just kind of, emphasize, check. I know how to do that one. I know how to do that one. I know how to do that one, yeah? And we would be good to go. Does that make sense? Sometimes, this is oftentimes referred to as a power reduction method of approach. We kept reducing down the powers. We had to, unfortunately, we ended up with an even power again. And when we had that even power show up again, we were forced to use the half angle identity a second time. Does that make sense? Okay. Let's do another example just to kind of drive this home. So again, if we had an odd power on sine or cosine, easy. If they're both even, then we have to start tweaking with the half angle formula, right? Until we get it down to a point that we can actually deal with. But this will systematically reduce down the powers. Let's do another one. Let's see. What if we did, okay, let's do something slightly easier potentially. Yeah, sir.
So when we have the problem before us, what is the end goal that we're trying to get to before we can?
We just want to have something that we know how to integrate.
And then we use integration by parts or not?
No, I mean, we wouldn't have had to use integration by parts on any of that, would we have? Where would we have had to use integration by parts on that? There's right, no integration by parts would be necessary on that list. I mean, I didn't finish the problem yet, but the point is, do you know how to do like the integral of 1? Yes. Integral of 1? Yes. What about the integral of cosine of 4x? Yeah, I mean, you might have to use a substitution, like put u equal to 4x, but certainly that one's doable also. It's just the antiderivative of cosine of 4x is 1/4 sine of 4x. Yeah, sounds very doable. So the end goal of this is just to be able to get to something that we know the antiderivative of. With the sines and cosines powers, I don't think you're ever going to have to do integration by parts. Now, you may have to do that when it comes to secant and tangent, but that's what we'll talk about tomorrow. Yeah. Yes.
What would happen if you use the Pythagorean identity on the so like you said, reduce using half angle identity. What would happen if you substitute?
Well, then you would have mixed matched angles. You see what I'm saying? Oh, what do you mean if I replaced
Like
sine squared with 1 minus cosine squared?
Yeah.
Well, you would still have the problem of having an even power. So for instance, I mean, we could do that. Watch. Let's do it. Okay. So what if all right, Daniel, let's do it here. So cosine squared of x, sine squared of x, dx. All right. What Daniel is saying is, hey, let's do this. 1 minus cosine squared of x dx. Yeah? Then we can't really do a substitution. So I tried to do like u equal to cosine of x. What do I not have anywhere? The sine, right? That you wouldn't have du anywhere, right? You wouldn't have the appropriate du. So what Daniel is saying is, okay, well, maybe I just distribute this thing. Okay, so like cosine squared of x minus cosine to the 4th of x dx, which in the end requires that I do a couple of integrals. So cosine squared of x dx minus the integral of cosine to the 4th of x dx. Do you know how to handle the first one? Like, how would you handle cosine squared? Half angle formula. Yeah? So you would kind of be, your hand would be forced anyways. You see what I'm saying? Okay, but let's, so this one right here is fairly easy. So let's actually do these two integrals. There's a minus sign between them. But let's actually do these two integrals. Hey, let's think about this. What in the world? What just happened? Add one here. So what about the integral of cosine squared of x dx? What would I replace cosine squared with?
Half.
Yeah, 1 plus cosine of 2x dx. And now we're in business. We actually know what those antiderivatives are, don't we? So, I mean, just write this 1/2 down. What's the antiderivative of 1? Okay. And it takes a little thinking here, but you could actually do that second one. You could do a u sub and put u equal to 2x, or you could just realize, oh yeah, it's basically sine 2x, but I need a factor of 1/2 to account for the chain rule, right? So it's going to be 1/2 sine of 2x plus a constant. So that wasn't too bad. What about that second one though? All right, so I go back over here. There was the cosine fourth of x that we had to deal with, yes? Okay, so it's here. So integral of cosine to the fourth of x dx. Well, yeah, it would, but I'm just kind of thinking about this separately. Yes, as it appeared in the last problem, yes, there would be a minus sign there. What am I going to do with this? What do you think?
Cosine squared.
Yeah. Cosine squared of x, quantity squared dx. Now what? Half angle formula. Okay, let me just slowly go through this. So it'll be 1/2 1 plus cosine of 2x squared dx. Okay, which is, let me just go down here. 1/2 squared is 1/4. Integral of, let's go ahead and square that other thing, because why not? You know what I'm saying? We're just going to square the 1 plus cosine of 2x. That's going to be 1 plus, okay, the cosine 2x, cosine 2x. So it's going to be how many cosine 2x's? Yeah, 2 cosine 2x's plus cosine squared of 2x. Ooh, dx. Okay. Uh-oh, what am I going to have to do again? Half angle formula, because I have the cosine squared sitting right there. You know what I'm saying? So then you would have 1/4 the integral of 1 plus 2 cosine of 2x plus, okay, now I'm going to replace this with 1/2 1 plus, I'm using the half angle identity on the cosine squared of 2x, cosine of 4x dx. And then you have to ask yourself, all right, do I know how to do all of these things? Do I know how to do 1? Yep. What about the 2 cosine of 2x? That's almost easier than the other one. It's actually just sine of 2x is the antiderivative of that, yeah, because the derivative of sine of 2x would be 2 times cosine of 2x. Perfect. All right, so I do know how to do that. What about the other stuff? Sure. The antiderivative of 1 is x. The antiderivative of cosine of 4x is 1/4 cosine of sine of 4x, yes? So I know how to do that, and I know how to do that. Okay, so we would be in business. So even if we did that, Daniel, we would still end up, it's like there's no, right, there's just a resistless compulsion to go to the half angle identities, no matter how clever we try to be. Okay? So the half angle identities is definitely a needful tool in dealing with even powers of sine and cosine, where that's exclusively what's happening. It's annoying, but it's necessary. Yeah. Right. So I mean, yeah, that's a good question, right? So I mean, okay. So if I had like the integral of sine of, the integral of sine of 76x dx. I mean, if you think about it, right, you could put u equal to 76x, then what's du? 76 dx. But so in other words, 1/76 du is what dx is, right? So that dx goes right there. You know what I'm saying? So then what would you have? You would have, I could pull out the 1/76, would be the integral of sine of u du. And now we're in business, right? What's the antiderivative of sine of u? Negative cosine of u, right? So this would be negative 1/76 cosine of u plus a constant, which is negative 1/76 cosine of 76x plus a constant. Right, so it's exactly that, yes? You have to be careful if the integral happens to involve sine, then you're going to have a negative cosine thing, but yeah. That's precisely what's happening, and that follows from just u substitution. It's true for sine and cosine because they're each other's derivatives, basically. Does that make sense?
So if I had like
Okay, so that's a little bit trickier because because the derivative of tangent, for instance, isn't exactly secant; it's secant squared, right? So in those cases, you just have to be a little bit more careful, and we'll deal with tangent and secant. That stuff is what's coming next. We're going to deal with that as a separate issue, but we just want to make sure we have our sine and cosine ducks in a row. Okay. So does the sine and cosine stuff make sense? Odd power. Somewhere on a sine or cosine, peel one off, switch to the other, do a u sub, we're good to go. Both even powers, that's the tricky one, but you just go with the half angle identities to kind of tip down the powers to something that we recognize. Okay? Any questions on that? This is your opportunity to ask. All right. Let's at least start the discussion on tangent and secant, and then we'll sort of finish with this. We'll at least start the discussion on tangent and secant, okay? This is going to get a little bit trickier, but I wanted to, first of all, I think there's one more thing I wanted to say about sine and cosine. It's right here, maybe this will be the last thing I say, I don't know. Okay, yeah, there's this, I don't expect you to memorize this. I just want you to be aware of it. It's actually in the book. Some of the stuff that we've been doing, right now, you can actually prove little definite integral formulas pretty easily by doing like an odd power of cosine and an even power of cosine. There's this amazing little formula, like if n is odd, it's something like you have the product of the evens up to one less than that, and then the product of the odds up to that thing. That's something called Wallace's formula. You can actually use Wallace's formula to approximate pi, actually, but you have to do it in the case of an even power. Here, like the evens and the odds have flipped. Do you see that? Okay. So it's a neat little formula. I think I actually have you apply it one time on WebAssign, just so that you have to use it at least once in your life. But it's a really nice formula, and it just follows from some of the stuff that we've done. I'm not going to force you to do this example. There's an example in WebAssign that you have to use that formula. Yeah. No, it's not only on that interval because cosine is periodic, right? I mean, so you could kind of move down the line if you wanted to. This is a very important formula for a variety of reasons. And it's just, I'm not forcing you to memorize it. I just want you to know that it follows from what we just did. Okay? All right. Let's at least start the discussion about products of powers of secant and tangent. Now, yesterday, we dealt with an obnoxious power of secant already, didn't we? By the way, it was much more comfortable when we had the even power of secant. You know what I'm saying? Secant squared, we're just like, boom, tangent. Yeah? But it was the odd powers of secant that seemed to be giving us trouble. It's kind of like the opposite of what happens with sine and cosine. Okay? The odd powers of secant are going to be troubling, okay, for the most part. But let's let's start with an example. We'll have sort of a set of rules that we'll follow eventually, but I just want to start out with an example and have us think through it together. But the key identity that we're going to use is the one we picked off yesterday. Mainly, it's just the Pythagorean identity, that secant squared is equal to 1 plus tangent squared. You might say, Pythagorean identity? What in the world? That must be a right triangle identity. It is a right triangle identity. Because, let me go over here. I'll show you what I mean. Okay, I don't know. This is kind of trigonometry in one picture. But if you draw the unit circle, so here's one like this, yes? Let me draw some stuff here. So if this is a point on the unit circle and it's at angle theta, okay? Then what you can do is you can draw in this thing right here, and this guy right here, this is sine of theta, okay? That y distance is sine of theta. Do you understand? What's the x distance called? It's cosine of theta. This, okay, so hang on a second. Let me just kind of extend this out a little bit because we need it. If you draw the tangent line, hint, hint, in this direction, okay, this angle right here is a 90-degree angle. Do you know what I mean? This length right here is 1. This distance right here, the distance from this point down to the x-axis, the tangent line, is called tangent of theta. Yeah? And this distance down here, what do you think that's called? That's secant of theta. Okay? So there's a couple of identities that are sort of obviously present here because of the Pythagorean theorem and all the right triangles floating around. Cosine squared plus sine squared is what? 1. You see it? Cosine squared theta plus sine squared theta is 1. But also on here is a little right triangle that's sitting on its hypotenuse of length secant of theta. Know what I'm saying? So the other one is that tangent squared theta plus 1, or 1 squared, if you will, is equal to secant squared of theta. By the way, there are some other distances in here. I'm telling you, you could go over it to Chuck's and kind of play with this if you want. But here are some other links. Like, for instance, if I go from this point up to here, that's another right triangle. Do you know what I'm saying? The distance from here, okay, so hang on. Tangent is the distance from the point down. The distance from the point up, that's called cotangent. Okay? And what do you think this distance is right here? Cosecant. Notice all this stuff on the left-hand side of the picture has has a little c's in front of it, right? You have cosecant, you have cosine, you have cotangent, and everything on the right-hand side is all the non-co stuff. You have secant, tangent, and sine. And there's all kinds of identities that come out of this automatically. For instance, it's obvious from this picture that cotangent squared plus 1 is equal to what? Cosecant squared. There's also even some weird identities. For instance, this is a giant right triangle right here. Do you see it? Yeah? Okay. For instance, you have cosecant squared plus secant squared is equal to the quantity cotangent plus tangent squared. Yes? That's a kind of a weird Pythagorean identity that just naturally follows from this thing. All of trig, polar trigonometry on the unit circle flows from this picture. All of it. Okay? You can just imagine that angle kind of moving and all of these things changing alongside of it. You can see that as the angle gets bigger, cotangent is getting smaller and tangent is getting bigger, yes? And you might be saying to yourself, hey, I thought that tangent was sine over cosine. Right? You might say, my teacher told me that tangent is equal to sine over cosine. Well, that's because you have a lot of similar triangles in this picture. Okay, and let me just show you for a minute. For instance, this angle's theta. If that angle's theta, what if I called this angle alpha right here? Okay. Then do you see like what has to be true about alpha plus theta? Yeah, that's 90 degrees. You know what I'm saying? Okay, that's got to be 90 degrees. So think about it. What is this angle right here? This angle would have to be alpha. Yeah? So what's true about that small right triangle and the big right triangle that's flipped upside down on its hypotenuse? They're similar. They have the same angles. Does that make sense? So for instance, you know that the angle opposite theta on the flipped upside down right triangle, or the side opposite, so tangent theta over 1. So think about it. If I take tangent theta, which is the leg opposite the angle theta, over 1, well, 1 is the side opposite alpha. Does that make sense? That has to be equal to, you go to this triangle right here that involves sine and cosine. What is the side opposite angle theta in this triangle? What's the side opposite theta? Sine. And what's the side opposite alpha?
Cosine.
Yeah? That has to be equal to sine over cosine. That's where the formula tangent equals sine over cosine comes from. Does that make sense? The only reason it's true is because those two triangles happen to be similar. And by the way, if this is theta, this angle is alpha. You know what I'm saying? And if that's alpha, then this is theta up here. There are tons of similar triangles in this picture. Yes, and you could exploit the similarities of all those triangles to get all kinds of ratio relationships. For instance, like sine is equal to, or secant is equal to 1 over the cosine. Yes, cosecant will be equal to 1 over sine. That will automatically follow just from kind of ratios of similar triangles type things. But the actual lengths are in the picture right there. And those like tangent equaling sine over cosine flows out of that picture. And the reason I'm showing you this is because a lot of people don't know this for some reason. I don't know if, like this, I remember the first time I saw this, I was like, man, I wish somebody would have told me that at some point. So I'm telling it to you, okay? This is all of trigonometry in one picture, basically. But we'll be using the tangent squared and secant squared one to kind of help us do the tangent and secant power integrals later. Do you have a question there, Jacob?
I was just thinking, is it possible to, so if you make another one beyond that, you're not trying to go outward?
I don't know. I mean, maybe, but I mean, no, I mean, these are the only links that one would actually really care about and kind of how the picture is changing. Yeah. All right.